In this video, we are going to look at the second part of integration by substitution as we look at definite integrals. So there are two ways to integrate definite integrals. One, well, let's read this. So when you use substitution to help evaluate a definite integral, you have a choice for how to handle the limits of integration. You can either do one of these, whichever is better for you. The important thing to remember is that the original limits of integration were values of the original variable, say x, not the values of the new variable, say u. So you can solve the antiderivative as a side problem and then translate your answer back to x's, and then use the antiderivative with the original limits of integration. Or you can substitute the limits of integration at the same time you're substituting for everything inside the integral. Then you can skip the translating back to x step. So if the original integral had the endpoints x equals a to x equals b, and you make the u substitution that u is some function g of x, and du is g prime of dx, then the new integral will have the endpoints of u equals g of a and u equals g of b. So we can either do it this way with the original integrand, or we can do it by substituting the former bounds into my u function to get the new bounds of integration. Let me show you what we mean. We'll do it both ways on these two examples. So let's integrate example 6, part A, where it says integrate from 0 to 5 of x over x squared plus 10 dx. Let's identify this x squared plus 10 as our u. Then our du, of course, would be 2x dx. So in my original integral here, I have the x and the dx, but not the 2. So we'll divide that 2 out. And what we'll have is 1/2 du equals x dx. So this x dx we do have here. That means here what we have, I'm going to leave the bounds the same and then we'll resubstitute later. This is that first method. We have the 1/2 we'll pull out front. That's this. We'll pull it out in front. And then the x dx is our u, or I'm sorry, du. And this is our u. Now we know to integrate du over u, that's just the natural log of u. So we're going to wind up with 1/2 times the natural log of u. And then we'll integrate that in just a moment. U we identified as being x squared plus 10. So we'll write 1/2. Oops, since we already integrated, we'll use a parentheses. 1/2 times the natural log of x squared plus 10. And we'll integrate this, from 0 to 5. So we resubstituted the x squared plus 10, and we're going to integrate from the original bounds. So we'll have 1/2 times the natural log of x squared, which is 5. So that would be 25 plus 10, or 35. Then minus 1/2 times the natural log of 0 plus 10, which is 10. We can punch that into our calculator and see what we get. Punching that into our calculator, we're going to get about 0.6264. Now, if we would have left this function in terms of u as we had here, then we could use the new bounds of integration, which would be, if we substitute 5 into x squared plus 10, we're going to get u for my upper bound would be 25 plus 10, or 35. So 35 is our upper bound. And then we'd plug 0 into the u. And we'd get 0 squared plus 10, which is 10. So my lower bound would be 10, and notice that's what we wound up having here anyway. This would also give us 1/2 times the natural log of 35 minus 1/2 times the natural log of 10. So it winds up being the same function. Let's do it. Let's first start and have you guys do problem B using the first method, where you resubstitute your u back into your function. And let's see what you get. Go ahead, pause the video and give it a try. Integrating B here, we'd have u be our 5 minus t, so du would be the derivative of 5 minus t, which is just a negative dt. So if it's a negative dt, we're going to pull that negative out front here, and we'll call this u to the 1/2 power. When we integrate u to the 1/2, we'll get, well, we have to remember to bring our negative over, so that's here, u to the 3/2, then divided by 3/2. But when you divide by a fraction, you flip and multiply to simplify. So this dividing by 3/2 becomes 2/3 multiplying. And it's negative because of the negative out front. And it will, when we resubstitute our u, which is 5 minus t, back in, we will have negative 2/3 times 5 minus t to the 3/2. And we'll integrate that from our original bounds because we resubstituted the 5 minus t back in. When you substitute a 1 in for t, you'll get 5 minus 1, which is 4 here. And then when you substitute a negative 4 in here, you'll get 5 minus a negative 4, which is 9. Doing the math on that, we get 12.6 repeating. Now, if you had not resubstituted the 5 minus t back in for u, you could change your bounds of integration and do it that way. So the upper bound, would have been the 5 minus t. So 5 minus 1 is 4. And we put that in here for u. And our lower bound would have been 9. So we'd take 5 minus, nope, I'm sorry. Our lower bound was a negative 4. So we'd take 5 minus a negative 4, which gives us the 9. And we wind up calculating the same thing we did above and getting 12.6 repeating. All right, let's go ahead and look at an application problem. Example 7 says the marginal price, P prime of X, at a supply level of X tubes per week of a certain brand of toothpaste is given by P prime of X equals 0.001 e to the 0.01 X. Find the price supply equation of if the supplier is willing to supply 100 tubes per week at a price of $3.65 each. How many tubes will the supplier be willing to supply at a price of $3.98 per week? Let's give it a shot. So in this problem, they're giving us the derivative function of price, and we need to integrate that to find the price function. And we'll find C by using the fact that when you have 100 tubes, so when X is 100, the price will become $3.65. So let's start by integrating this function, 0.001 e to the 0.01 x. Now often we'll move and this is integrating with respect to x, so we'll throw that in there. When you have a constant, we move it out front, so we have 0.001 times the integral of e to the 0.01 x dx. When we integrate using substitution, we let the inside function be our u, so we'll say u is 0.01 x, then du would be 0.01 dx. So we don't have the 0.01 here, so what we're going to do is divide both sides by 0.01. When we resubstitute our u back in here, then my constant out front will become the 0.001 divided by this 0.01. And in here, we'll have e to the u du. Now all we have to do is integrate e to the u, which we know becomes just e to the u plus c. But what about this? On your calculators, go ahead and take 0.001 and divide it by 0.01. You may be surprised what you get. 10, right? No, 0.1. Yep, so this out here just becomes a 0.1. So we'll write that. So my price function becomes P of X equals 0.1 e to the u. Remember, u is 0.01x, and then plus c. But they told us that when x is 100, the price was $3.65 each. So we're going to put that in here to solve for c. And we're substituting in 100 for x. What we'll get here then is E 3.65, 0.1 E. If you multiply these out, you just get to the first. So if we subtract, we will find out what C is. 3.35 minus 0.1 E. And you get 3.078. Or we'll call that 3.08 because this is a price and we'll round to the nearest cent. So our price function becomes 0.1 e to the 0.01x plus c, which we found to be 3.08. Then it wants to find out how many tubes would the supplier be willing to supply at a price of $3.98. $3.98 is the price, and we'll go into the left side of our function. 0.1 e to the 0.01x plus $3.08. Now we solve for x. So if we subtract $3.08 from both sides, we're going to get just 90 cents over here, and that will equal 0.1 e to the 0.01x. To solve this, we want to isolate the e, so we'll divide by 0.1. And we'll get 9. To solve this, we know we need to convert to a log. So let's convert this to a natural log. So the natural log here of 9 will equal 0.01x. To solve for x, we divide by 0.01. And we'll get oops, let's see. $219.722. So what this means is at a price of $3.98, you'd want to produce about 220 tubes of toothpaste. All right. Thanks for watching, and we'll see you in the next video.